You type a simple question into the blank text prompt. What is the capital of Australia? And then you hit enter. In the silent pause that follows, we instinctively imagine a machine at work, searching an internal library or retrieving a specific memory. The machine operates without a central archive or a database of facts. It possesses no mechanism to deliberate over the truth. Every step of the process is a mathematical calculation, the production of a probability distribution to determine the single most likely token to generate next. The intelligence we project onto that blinking cursor emerges from this structural calculation, the statistical prediction of a sequence. To see how this works, look at the model's vocabulary. It consists of tens of thousands of individual tokens, pieces of words, punctuation, and spaces. In the fraction of a second before the response appears, the machine evaluates the entire grid. Immediately, the vast majority of those tokens drop out with a near-zero probability. They are mathematically irrelevant to your question. The probability mass concentrates on a tiny cluster of plausible continuations. Here, the highest probability token is Canberra, assessed at a 38% likelihood. Another strong possibility is the word the, sitting at 22%. It's a grammatical stepping stone toward a phrase like the capital is. But further out in the cluster, the word Sydney quietly holds a 4% probability. Sydney is the largest city in Australia, not the capital. However, the human text used to train the model contains countless examples of people making that exact geographic mistake, rendering it a plausible sequence. The distribution maps the patterns of human writing. It rewards plausibility based on historical data, remaining blind to factual truth. Having mapped out these probabilities, the machine must now make a choice. It does not automatically lock on to the highest percentage every time. The strictness of this choice is governed by a setting called temperature. This parameter introduces a calculated amount of randomness into the selection process. At a standard temperature, the system will usually pull the top token, but if you roll the dice enough times, then eventually the selector lands on the lower probability option, Sydney. The instant Sydney is selected, it is appended to the original prompt. The entire vocabulary grid resets, recalculating a fresh probability landscape for the second word based on that new input. Pick a token, add it to the sequence, recalculate the distribution. This loop fires over and over again until a complete response is formed. If you ask the same prompt twice and get a different response, the AI hasn't changed its mind. You are watching the mathematical variation of sampling in real time. Back on your screen, the output appears seamless. The AI produces a fluent, well-structured paragraph naming Sydney as the capital of Australia. It writes with authority, using words like definitely and certainly. It selects these stylistic markers because, in its training data, they frequently follow declarative statements. The model's confidence is decoupled from its accuracy. High token probability tells you about the style of the text it's generating, not the factual weight of the claim. Because the underlying mechanics are identical, whether generating an accurate fact or a lie, the tone of the response offers no proof of its validity. The token-by-token distribution we see at the surface is the final stage of output. Behind that interface, substantial computation shapes the probabilities. This text outlines how advanced reasoning models do additional work before outputting anything. They generate hidden intermediate tokens, often called a thinking phase, which rely on attention patterns and deep internal representations to condition the final visible output. These internal regularities encode an enormous amount of human data, functioning much like knowledge. But the final result pushed to your screen remains a sample drawn from a calculated distribution. The machine possesses no internal mechanism to verify its own facts. It only confirms that the sequence of words it just printed is mathematically plausible. It never deliberates. It never lies. It simply computes the plausibility of the next word, completely in the dark.